This is a representation of Earth's magnetosphere and ionosphere, which begins about 50 kilometers above Earth's surface and becomes more apparent around 70 to 80 kilometers. This is the ozone layer, which forms due to chemical reactions within Earth's atmosphere. The ozone layer is most distinct between 15 and 35 kilometers of Earth's atmosphere. Every day, we are bombarded with high-energy radiation from the sun, comprised but not limited to gamma rays and cosmic rays, which are defended by Earth's magnetosphere and ionosphere. This region experiences substantial electrical activity and is where atmospheric gases absorb this small wavelength radiation, ionizing into electrons and positive ions which can interact with other molecules within the air. Ions and electrons produced at high altitude are free to diffuse downward, guided by Earth's magnetic field and traveling back and forth between the poles. Several mechanisms are known to contribute to the destruction of ozone within the stratosphere. For this video, I would like to focus on the area of the Antarctic polar ozone hole. The ozone hole has been of considerable focus over the last decade due to the increasing size and depletion, which allows for dangerous UVC and UVB radiation to reach Earth's ecosystems. The question I am most interested in is, how does solar radiation affect the depletion of ozone within Earth's atmosphere? In class, we learned that the destruction of ozone is altitude dependent, and both NOx and halogens are significant players in the destruction of odd oxygen within the stratosphere. Through these two loss cycles, we see that NOx plays a significant role in the loss of odd oxygen within the stratosphere, especially within the mid-latitudes. Nobel Prize winner Paul J. Crutzen first identified a large production of NOx in polar ice cap regions due to charged particles making their way poleward during solar proton events, which he hypothesized would result in subsequent ozone loss. The first data for such an event from a solar proton event first occurred in 1972 on August 4th, where a flux of nearly 60,000 protons per centimeter squared per second per radian squared was measured by Pioneer 9 spacecraft. This resulted in up to 20% ozone reduction at 45 kilometers after 19 days previous from the average of ozone in the stratosphere at that height 7 days before the August 4th event. This is a significant decrease in ozone, and this event of such magnitude should not be overlooked. So we've learned that solar proton events can significantly affect the depletion of atmospheric ozone within the mid-stratosphere on a shorter lifetime. But what about a longer lifetime? And how does this impact the minimum column ozone concentrations that have been measured, which are used to describe the ozone hole? And how does this impact the minimum concentrations observed within the data sets? So here are two data sets from NASA looking at ozone hole area and minimum ozone concentrations in the months of September and October. And we can see for two large solar events, one between 1989 compared to the previous year in 1988, we see a drop of nearly 44 Dobson units between the minimum ozone concentration measured. We also see an increase of nearly 8.7 million kilometers squared in 1989 compared to 1988. This is a large magnitude, but what about other events? We also see that in 2003 there's a large difference in minimum ozone from the previous year in 2002, where nearly 50 Dobson unit drop from the previous year and another 13 million kilometers squared increase in ozone hole area. But does this hold true for all events? We see in 1987, in comparison to the previous year, that there's nearly a 24 Dobson unit decrease. However, only 120 solar proton flux was measured for that year. Also, in 2001, we see nearly no decrease from the previous year and an increase in the following year. And so how can we determine what these lifetimes of these events are on the concentrations of ozone within the stratosphere? Lastly, Can we develop recovery rates from years which receive no solar radiation to deduce the impact of halogens versus native NOx processes and better understand the lifetime of these events? I think more information would be needed and more analysis would need to be done. Thank you.